Hey everyone, welcome back to Heriverse. If you enjoy mysterious science and cosmic stories like this, please remember to like the video, subscribe to the channel, and share it with a friend who loves space. It really helps Heriverse grow, and I appreciate your support so much. Before we dive into today's journey with 3i Atlas, I'd love to know, what time are you listening to this, and where in the world are you right now? Let me know in the comments. I read everyone. All right, let's begin. On a cold midwinter day in late January of the year 2026, an unusual alignment settles quietly over the inner solar system, far from Earth, yet not so far that the great observatories can ignore it. The interstellar visitor known as 3i Atlas passes into a geometry that astronomers rarely have the chance to witness. The Sun, Earth, and the object line up almost perfectly, so that from the planet, the comet-like body appears fully illuminated, similar in principle to a full moon. Every visible side that can reflect sunlight toward Earth now does so. There is almost no shadowed portion hidden from view. For a brief window of time, 3i Atlas stands in what observers call full phase, turned toward the planet like a bright, unresolved disk wrapped in a hazy envelope of dust. The timing is deliberate only in the sense that orbital dynamics leave no room for choice, yet the coincidence feels sharply focused. Days earlier, astronomers have calculated that the object will pass almost exactly behind the Sun, from Earth's perspective offset by noticeably less than a single degree. That is a narrow lane in the sky, the sort of alignment that very rarely occurs even for familiar members of the solar system. For an interstellar body, one that arrives from the depths between the stars, the rarity is even more striking. The alignment becomes exact on January 22nd. While clouds drift over many observing sites on Earth, a different kind of eye remains clear and steady above the atmosphere. The Hubble Space Telescope has been aimed toward 3i Atlas with careful planning. Hubble carries instruments that measure brightness, resolve delicate structures in diffuse light, and trace how gas and dust behave in the faint surroundings of distant small bodies. Now, as the alignment peaks, the telescope records image after image of the fully lit visitor. At first glance, the data seem to confirm what some astronomers have argued since the object was discovered. 3i Atlas behaves like a comet, a body of ice and dust that releases material as sunlight warms its surface. There is a diffuse glow where fine grains scatter light, and the overall shape resembles a small, bright core embedded in a spreading cloud. Yet even in these initial frames, a different feature draws the most attention. Extending not away from the Sun but toward it, a thin plume of dust forms what is known as an anti-tail. In ordinary comets, tails appear to stream outward on the night side, pushed away by solar radiation and the outflow of charged particles from the Sun. In this case, at least from the vantage point of Earth, the dominant feature points almost directly back along the line to the star. It seems to defy the usual expectation of a cometary tail and challenges the simple picture that dust always trails behind. The underlying physics allows such features. When a comet moves along its orbit, dust grains released earlier can follow their own paths, sometimes forming structures that, when viewed from certain angles, appear to point sunward, even though the grains themselves are being pushed away. 3i Atlas finds itself in just such a geometry. The anti-tail arises from alignment and perspective, but the context matters. The visitor is not a long-known family member from the distant Oort cloud surrounding the Sun. It is an interstellar object entering the system on a hyperbolic path from far beyond the realm of the planets and leaving again after only a brief passage. The combination of an interstellar orbit and this rare full-phase alignment gives every subtle detail an additional weight. Small deviations from expectation do not simply refine models of comet behavior. They touch directly on questions of how matter is arranged beyond the solar system and whether some of it, in rare cases, might not be entirely natural. In the hours following the observation, preliminary analyses circulate among research teams. Brightness curves are extracted from the images, tracking how the total light from the object rises as it comes into full phase and then slowly declines. In a full-phase configuration, the illuminated area is maximized, so even small changes in surface or dust properties can produce noticeable shifts in brightness. Astronomers watch for a surge, a sudden increase corresponding to the exact moment when the object is fully illuminated from behind the observer. They also look at how steeply the light rises and falls. From these changes, they hope to infer the texture of the dust, the size of the grains, and the way the surface releases material. Bright, fine grains behave differently from darker, larger chunks. By mapping how 3i Atlas brightens, the teams attempt to separate these possibilities. What emerges from the early results is a pattern that is interesting, but not yet conclusive. The brightness does increase as expected, yet some of the fine structure in the light curve hints at more than a smooth, uniform surface. There are hints of preferred regions, jets, and structures that come in and out of view as the object rotates. That rotation has already been estimated from earlier data taken when the object was closer to Earth. Periodic variations in brightness combined with subtle changes in the orientation of outflowing material indicate that 3i Atlas spins roughly once every 7 hours. Even without resolving the nucleus directly, astronomers can use this regular modulation as a kind of heartbeat, a measure of the object's internal rhythm. During the full phase alignment, that rhythm interacts with the geometry in revealing ways. As the object turns the anti-tail and any embedded jets change their apparent shape and brightness. Some frames show the sunward plume more strongly, others less so. A careful reconstruction of this changing pattern promises to reveal how the jets are arranged on the hidden surface and how they connect to the overall rotation. From a scientific point of view, this is an extraordinary opportunity. The full phase view removes the complexity of partial illumination. With no large portion of the nucleus in shadow, modelers can focus on how the brightness changes purely with angle and time, rather than trying to correct for unseen sections. The alignment effectively turns 3i Atlas into a natural laboratory for studying the way interstellar ice and dust respond to sunlight. At the same time, the rarity of the geometry introduces a quieter tension. It is one thing for a random object from the distant dark to pass briefly through the inner system. It is another for it to do so in a way that places it almost exactly behind the sun from the only inhabited world in reach at the very moment when the world's most powerful telescopes are ready to observe. Each of these facts has a conventional explanation. Surveys now monitor large stretches of the sky, so unusual objects are more likely to be found. Once discovered, they naturally become targets for major observatories. Orbital alignments, even rare ones, are inevitable given enough time. Yet, when all of these circumstances converge on a single interstellar visitor, the human mind does not easily dismiss the sense of design. The documentary lens lingers on the images, a small bright point wrapped in a faint halo, a delicate plume pointing toward the sun as if marking the axis of alignment. No dramatic conclusion follows, only the recognition that something improbable has unfolded, according to laws that remain fully natural and yet feel newly charged. The alignment of January 22nd becomes the opening chapter of a developing story, a reference point to which later observations will return. As the data from Hubble and other observatories continue to be processed, the scientific community holds a shared understanding that this moment when 3I Atlas turned its fully lit face toward Earth and displayed a sunward plume may contain the first clear clues to a deeper mystery yet to be uncovered. As the world spins through the hours following the exact alignment, the first substantial analysis of the Hubble data begins to circulate among a small circle of specialists. The images taken around January 22nd show 3I Atlas fully illuminated without the confusion of deep shadows along its surface or within its surrounding cloud. In each frame, the object appears as a compact, central glow, enveloped by a broader, roughly spherical haze, with the sunward anti-tail cutting through this diffuse light as a more structured feature. Automated pipelines calibrate the raw images, removing instrumental noise and correcting for distortions introduced by the optics. Astronomers then extract brightness profiles tracing how the intensity of light falls off from the center toward the edges. In a typical comet, these profiles follow familiar shapes, with the densest dust near the nucleus and a gradual thinning outward. In the case of 3I Atlas, the broad pattern is recognizable, yet the details resist an easy fit. When researchers subtract a model of a smooth spherical glow from the images, residual structures emerge. Some of these are expected, such as the anti-tail and subtle asymmetries caused by the object's motion through the solar wind. Others appear less straightforward. Narrow enhancements in brightness cling to particular directions, suggesting confined jets rather than a uniform outflow. The full phase geometry sharpens these differences because every emitting region that faces the sun now also faces the line of sight to Earth. Under these conditions, even modest variations in dust density or grain properties can translate into measurable signatures in the light. The Hubble observations, combined with parallel measurements from ground-based telescopes on those parts of Earth not shielded by cloud, begin to chart the behavior of 3I Atlas over many hours. Teams examine how the total brightness changes, with time searching for the surge that should accompany the transition into exact full phase. A clear increase is present, consistent with the idea that more of the surface becomes visible as the geometry tightens. However, the rise is not perfectly smooth. Superposed on the general brightening are smaller fluctuations that repeat with a regular cadence reflecting the known rotation period of roughly 7 hours inferred from earlier campaigns. This repetition confirms that the object is indeed spinning, and that parts of its surface are more active than others. As particular regions rotate into direct view, the contribution of their dust and gas increases the total brightness in small but noticeable steps. At the same time, subtle changes in the appearance of the anti-tail suggest that the sunward plume is not a simple static structure. The alignment effectively locks the direction to the sun and to Earth into nearly the same line, so any variability in the anti-tail cannot be blamed on changing viewing angles. Instead, it must arise from processes within the object itself, such as variations in the rate at which dust is released or the pattern of underlying jets feeding the plume. This is where the data begin to strain comfortable expectation. When astronomers model ordinary comets, they allow for irregularities in the surface pockets of ice that turn to gas when heated and fractures that channel material into space. These features produce jets that may come and go flare as the comet turns and spread out under the combined influence of gravity and solar radiation. Such models can often reproduce complex brightness patterns. For 3i Atlas, the full-phase observations demand a configuration in which the most prominent outflow points almost exactly along the line from the object to the Sun, and during this alignment, almost exactly toward Earth. Moreover, when the underlying spherical glow is filtered away using techniques designed to isolate fine structure, the residual pattern reveals 3 distinct jets separated by approximately equal angles around the unseen nucleus. This triple symmetry is inferred rather than directly imaged, yet the residual light distribution is difficult to explain without invoking 3 main sources spaced roughly equally in longitude on the surface. The combination of a sunward anti-tail and 3 apparently evenly separated jets around the nucleus forms the core of the emerging puzzle. The full phase data reinforce it. With the entire sunlit side exposed, any imbalance in the distribution of dust should become more obvious. The persistence of the triple structure through the bright phase, with the anti-tail dominating the sunward direction, suggests an underlying organization that is not easily produced by random fractures or sporadic venting. At this stage, the interpretation remains cautious. Researchers test whether simple models of natural processes can account for the observations. They vary the size distribution of the dust grains from fine particles that strongly scatter sunlight to larger chunks that respond more sluggishly to radiation pressure. They adjust the composition, exploring mixtures of dark and bright material, and consider the possibility of complex surface topography that channels outflow into preferred directions. In many cases, they can reproduce parts of the behavior, but not all of it at once. Some models generate an anti-tail of the right general appearance, but fail to produce a stable 3-jet pattern. Others yield a geometry that resembles 3 jets, but require fine-tuned surface features that remain speculative. The brightness surge itself carries additional information. The rate at which the light increases as 3i Atlas enters full phase depends not only on the surface area illuminated, but also on the texture of the dust that blankets the nucleus and fills the surrounding cloud. Smooth, compact grains scatter light differently from porous, fluffy aggregates. Astronomers know from studies of solar system comets that these properties can be inferred by measuring how brightness and polarization change with phase angle, the angle between the Sun, the object, and the observer. In the case of 3i Atlas, the phase angle on January 22nd shrinks to a small value, making it possible to probe the so-called opposition effect, a phenomenon where certain surfaces brighten disproportionately as shadows between grains disappear. Clues from polarization. The preferred orientation of the electric field of scattered light also become important. Though not all instruments are optimized for this, some observatories can measure how the polarization changes as the object moves through different phase angles in the days before and after full alignment. Early indications suggest that the dust around 3I Atlas does not behave identically to typical cometary dust. The opposition surge appears stronger than expected for standard mixtures, and the polarization pattern shows subtle deviations. These are not dramatic enough to demand exotic explanations, yet they add to the sense that this visitor is not simply a copy of familiar comets transplanted from the outer solar system. The full-phase observations also underscore the limitations of the current instruments. The Hubble Space Telescope, despite its precision, cannot resolve the nucleus of 3I Atlas at its current distance. The central glow remains a blurred point enlarged by the telescope's optics and the scattering cloud of dust. Any solid body hidden within remains below the threshold of direct imaging. This leaves the structure inferred from the behavior of the surrounding material. Astronomers strip away the spherical component of the glow using mathematical filters that attenuate smooth emission and enhance narrow features. What remains after this subtraction is the network of jets, the anti-tail, and the fine asymmetries that hold the clues to how the object works. Within the filtered images, the three jets that persist around the nucleus stand out as a particularly regular pattern. They extend outward like three spokes in a wheel that is otherwise hidden, separated by roughly equal angles. The anti-tail appears as an extension of one of these structures along the sunward line. To some, this regularity suggests an internal architecture, perhaps deep fissures or aligned regions of volatile material arranged in a repeating pattern. To others, especially those attuned to the possibility of technological artifacts, the symmetry recalls engineered systems such as thrusters arranged to control motion along multiple axes. The documentary tone remains measured, yet the underlying tension is clear. The Hubble data gathered during a brief window when cosmic geometry allows a full view of the sunlit side do not deliver a simple verdict. They confirm that 3I Atlas releases dust and gas like a comet, that it brightens in a way consistent with full-phase illumination, and that an anti-tail can be understood as a product of alignment and particle dynamics. At the same time, they reveal a jet system whose symmetry is unusual, possibly unique, and whose persistence through the bright phase hints at an organizing principle that is not yet understood. The full alignment does not resolve the mystery, it sharpens it. Now, as the object moves away from the exact Sun-Earth line and the phase angle slowly grows, the attention of the scientific community turns to the next stage of analysis. Time series of brightness, polarization, and jet orientation will be compared with models of rotating bodies, and the inferred spin axis will be checked against the line of sight from Earth. If the axis is indeed closely aligned with both the Sun and the planet during the full phase, as preliminary work suggests, then the image of 3I Atlas as a kind of cosmic lighthouse spinning and directing its structured outflow along a narrow corridor through space will take on new significance. The data gathered under full illumination are only the first layer of this emerging picture. Beneath them lies a deeper pattern that promises either to reaffirm the flexibility of natural processes or to push the boundaries of what is considered plausible for a purely natural object. Well, before the rare full phase of January 22nd, 3I Atlas has already begun to reveal its internal rhythm. In the months leading up to the alignment, as the object passed closer to Earth, observatories across the planet tracked its brightness night after night. When the total light from a small distant body is recorded over many hours and days, subtle patterns sometimes emerge, gentle rises and falls in brightness repeating with a regular period can indicate rotation as different faces or active regions of the object turn into and out of view. For 3-eye atlas, this kind of monitoring produces a clear signature. The measured light does not remain constant. Instead, it waxes and wanes in a repeating cycle that lasts on the order of 7 hours. This periodic variation combined with changes in the appearance and orientation of the dust structures around the object leads to the conclusion that 3-eye atlas rotates roughly once every 7 hours, about an axis that remains fixed in space on human time scales. The rotation period is not inferred from brightness alone. High-quality images, though unable to resolve the nucleus itself, show the faint jets and plumes in the surrounding dust shifting their apparent direction over time. A jet that appears to point slightly northward in one sequence of images is seen leaning slightly in another, as if the source from which it emerges is slowly turning. When these changes are matched to the brightness variations, a consistent picture forms. The nucleus carries a system of vents or fractures that release gas and dust in preferred directions, and as the solid body rotates, these jets sweep through space, changing the shape and brightness of the surrounding cloud. The analogy to a lighthouse, while simple, is useful. A lighthouse beam appears to sweep across the sea because the source of light rotates, not because the beam itself bends. In the case of 3-eye atlas, the narrow jets act as beams of escaping material. As the object turns, the jets trace out cones in space, and their projections on the sky wobble in a repeated pattern that matches the roughly 7-hour rotation period. This interpretation gains further strength from the full-phase observations. When the object is fully illuminated, the changing sunlight angle no longer complicates the view. Any wobble in the jets can more confidently be attributed to the rotation of the nucleus, rather than shifting illumination. Under these conditions, the data show that the main structures in the dust indeed repeat their positions with the same rough period inferred earlier. The rotation is real, coherent, and persistent. The next question is how the rotation axis is oriented in space. For a randomly oriented object, the axis could point in almost any direction with no preference for aligning with the Sun, Earth, or any planet. In the case of 3-eye atlas, careful modeling of the jet wobble suggests a different, more surprising arrangement. When astronomers attempt to reproduce the observed changes in jet orientation, they find that the best fits are obtained when the rotation axis points close to the line joining the object and Earth, and also close to the line joining the object and the Sun, during the period around January 22nd. In other words, during the rare full-phase alignment, the spin axis appears nearly aligned with both the Sun and the planet. This configuration means that the object spins much like a top, whose axis is almost directly aimed at the observer. When a top is viewed from above, its surface features do not swing in wide arcs across the field of view. Instead, they circle around a point near the center. Similarly, for 3-eye atlas jets attached to regions near the poles of the rotation sweep around in space, but from Earth's perspective remain confined to modest changes in position. This geometry has a significant consequence for the anti-tail. If one of the main jets or groups of jets happens to lie close to the spin axis, then the material it releases will on average be directed along that axis as the object rotates. During the time when the axis itself is nearly aligned with the Sun and Earth, such a jet will point within a small angle both sunward and along the line of sight to the planet. The anti-tail then appears not merely as a consequence of dust dynamics and perspective, but as the visible expression of a jet that is at that moment in the orbit almost aimed at Earth. This possibility captures attention. A natural object with a jet that happens to line up with its spin axis and with the Earth-Sun direction during a rare alignment is not impossible, but it is statistically unusual. The laws of gravity and motion do not forbid it, yet they do not require it either. The data suggest that the anti-tail is fed by a jet or system of jets that is closely tied to the rotation axis. The wobble of this structure modest but detectable traces out a pattern consistent with a nearly pole-aligned outflow. When this is combined with the full phase geometry, the result is an anti-tail that seems to swing toward Earth, not because the object responds in any way to the planet, but because the pre-existing internal structure happens to be oriented in this rare way at this particular time. From a scientific standpoint, this is an extraordinary coincidence to study. From a more speculative standpoint, it invites questions about whether there might be more to the alignment than chance. Before such questions can be entertained seriously, another concern must be addressed. If a jet is effectively pointing toward Earth releasing gas and dust that includes substances such as cyanide, is there any real hazard to the planet? Here, the calculations offer reassurance. 3. I-Atlas moves through the solar system at a speed of roughly 60 kilometers per second relative to the Sun, a velocity typical for an interstellar object on a hyperbolic trajectory. The gas and dust released from its surface initially share this motion, then are further accelerated away from the Sun by radiation pressure and the solar wind, the stream of charged particles flowing outward from the star. The combined effect is to carry most of the material away from the inner regions of the solar system and out of the orbital plane where Earth travels. Detailed orbital calculations trace the path of the nucleus and the envelope of possible dust trajectories. The result is that, despite the striking visual impression of a jet pointed almost directly along the line of sight, the actual particles do not intersect the Earth's orbit. The object never physically crosses the circular path that the planet takes around the Sun, and the dust released around the time of the full phase is carried away in directions that avoid the region of space that Earth occupies. Toxic molecules, including cyanide, are indeed present in the outflow. Such compounds are common in cometary material and have been detected in other bodies visiting the inner solar system. In the case of 3I Atlas, the concentration appears substantial, but the distances involved and the dynamics of light and charged particles ensure that none of this hazardous material reaches the planet in meaningful quantities. The apparent targeting suggested by the anti-tail is therefore a matter of alignment rather than intent. The scientific narrative emphasizes this point. The geometry is unusual, the configuration statistically rare, but the physical processes that protect Earth are well understood. The object moves swiftly through space-shedding material that is then swept away by the Sun's influence. In this sense, the swing of the anti-tail toward Earth is an optical phenomenon shaped by perspective and the interplay of rotation and illumination, rather than a genuine threat. Still, the alignment of the spin axis with the Earth-Sun line remains an intriguing detail. Astronomers examine whether observational bias could favor the detection of interstellar objects with such orientations, but no obvious mechanism emerges. They test models in which the internal structure naturally channels volatile material along the axis, perhaps due to structural weaknesses or inherited anisotropies from the object's formation in another planetary system. They consider whether long-term torques from outgassing could have gradually reoriented the spin axis into its present position as the object approached the Sun. Some of these ideas remain plausible. Outgassing can indeed change the spin state of small bodies over time, and an interstellar visitor moving through varied environments might undergo complex rotational evolution. However, the specific coincidence of a nearly aligned axis at the moment of a rare full phase remains hard to reproduce in generic models. A different perspective arises from the community that studies possible technological artifacts. For such researchers, a spinning object whose outflow is organized around a principal axis, with jets that appear in a symmetrical pattern and an anti-tail that aligns with a line connecting a star and a habitable planet, invites comparison with engineered systems. In spacecraft, design thrusters are often arranged to generate torques and controlled forces along chosen axes, allowing precise adjustment of orientation and trajectory. A system of 3 jets spaced equally around a spin axis can in principle provide control in a plane perpendicular to that axis, while an additional component along the axis can influence motion in the 3rd dimension. Within this framework, the observed combination of a triple jet pattern and a polar anti-tail naturally mirrors certain control schemes. The documentary voice keeps these ideas at arm's length, presenting them as one possible way to interpret the geometry, rather than as conclusions. The known facts are laid out clearly. 3. I-Atlas rotates roughly once every 7 hours. Its rotation axis appears to lie close to the line connecting the object, the Sun and Earth, during the full phase of January 22nd. The most prominent dust plume forming an anti-tail points along this axis toward the Sun, and in that brief window, almost directly along the line of sight to Earth. The jet system inferred from filtered images displays an unusual symmetry with 3 main components separated by roughly equal angles around the nucleus. The outflow contains toxic materials such as cyanide, yet the trajectories of the dust and gas combined with the object's rapid motion and the influence of solar radiation ensure that none of this hazardous material reaches the planet. These are the data. Beyond them lies interpretation. Is the alignment a rare but natural coincidence produced by the interplay of rotation internal structure and orbital mechanics, or is it a subtle indicator of some controlling principle, perhaps even a sign of technological origin? For now, the scientific community leans toward natural explanations, while acknowledging that the detailed models needed to reproduce all aspects of the behavior are still incomplete. The wobbling jets, the near alignment of the spin axis, and the sunward anti-tail aimed along the Earth-Sun line remain as linked features in a developing story. They mark 3I Atlas, not only as an interstellar visitor, but as a rotating beacon whose beams, whether carved by chance or design, brush momentarily across the small blue world that watches from afar. As the early analyses of brightness and rotation circulate, attention turns increasingly to the fine structure of the dust around 3I Atlas. The raw Hubble images and supporting ground-based data show the familiar combination of a bright inner glow surrounded by a diffuse halo. Yet much of the most interesting information is hidden beneath that smooth appearance. To uncover it, astronomers rely on specialized filtering techniques that suppress the nearly spherical component of the light and enhance narrow, elongated features. Among these methods is a class of filters designed to subtract a symmetric envelope from an image, leaving behind only those structures that deviate from simple radial profiles. When such a filter is applied to the images of 3I Atlas taken around the time of the full phase alignment, the transformation is striking. The broad, hazy glow that dominates the unprocessed frames is largely removed, and in its place, a cleaner pattern emerges. At the center sits a compact core still unresolved, but less obscured by the surrounding light. From this region, 3 narrow jets extend outward into the halo, arranged in a pattern that appears remarkably regular. They are separated by roughly equal angles, each one offset from the next by about 1/3 of a full circle. The anti-tail, previously seen as a general sunward plume, can now be interpreted as an extension of one of these jets along the axis that points toward the sun and during the alignment toward Earth. The visual impression is of a 3-spoke structure radiating from a hidden hub, with one spoke aligned with the principal external direction set by the sun. This pattern does not occur frequently in images of ordinary comets. In most cases, jets emerge from irregular surface regions guided by fractures, local topography, and compositional inhomogeneities. The resulting structures may be numerous, but rarely fall into such simple, evenly spaced arrangements. 2 dominant jets may appear perhaps roughly opposite each other, or a more chaotic array of many small outflows may blend into a complex fan. A system of exactly 3 jets separated by similar angles and persistent over the timescale of weeks is much less common. The persistence itself is a clue. If the pattern were transient, perhaps produced by a brief episode of activity in 3 unrelated regions of the surface, it might be easier to attribute to chance. Instead, data from multiple nights processed independently tend to reveal the same triple configuration. The jets may vary in brightness as the rotation of the nucleus changes their orientation relative to the sun, but their relative spacing remains within the limits of the measurements close to equal. Astronomers trying to interpret this behavior turn first to natural explanations. They imagine a nucleus carved by ancient stresses, perhaps fractured into 3 main sectors, in which volatile material is more exposed with each sector feeding a dominant jet. They model surface shapes that include 3 broad depressions or clefts, separated by ridges so that gas and dust are preferentially channeled into 3 directions that maintain roughly equal separation as the object spins. Such a geology is not impossible, especially if the object has undergone repeated thermal cycles in its history, either in its original planetary system or during an earlier passage through another star's environment. Yet, for an interstellar visitor, whose formation history is unknown and whose surface cannot be seen directly, each such model remains conjectural. The symmetry of the jets demands a degree of internal organization that simple random fracturing does not easily supply. At the same time, the full-phase observations constrain how these jets relate to the rotation. As discussed earlier, the inferred spin axis lies close to the line of sight during the January alignment. Under this geometry, jets anchored near the equator of the nucleus, would sweep out broad arcs on the sky as the object rotates, producing patterns in the filtered images that change dramatically from one observation to the next. Instead, the triple jet structure appears stable in its relative arrangement, consistent with sources that sit at roughly similar latitudes and maintain their angular separation as they rotate around an axis approximately pointing toward the observer. This suggests that the three jets are tied to a coherent, possibly global structure on the nucleus, rather than isolated active spots that turn on and off. The anti-tail adds another layer of complexity. If one of the three principal jets aligns with the spin axis during the full phase, then the dust it releases will on average follow trajectories close to that axis. Because the axis itself is nearly aligned with the Sun and Earth. At this time, the resulting plume will appear as a narrow sunward extension, forming the observed anti-tail. Meanwhile, the other two jets, separated by about 1/3 of a circle from the first, will project onto the sky as off-axis features, contributing to the symmetric pattern around the nucleus. The combined result is a threefold geometric arrangement, with one element singled out by its orientation toward the Sun. When seen through the lens of natural comet physics, this is a remarkable but potentially explainable configuration. When viewed from a different perspective, it begins to resemble something more deliberate. Within the community of researchers exploring the possibility of technological artifacts in space systems of jets that are both symmetric and aligned with a spin axis are of particular interest. In engineering terms, arranging thrusters or outgassing vents in a regular pattern can provide controlled torques and forces to manage rotation and trajectory. Three sources equally spaced around a central body can, if properly modulated, stabilize orientation along two perpendicular directions. If a fourth component, such as a dedicated outflow along the spin axis, is present, it can influence motion along the third dimension. In this view, the triple jet system of 3i Atlas, with an associated anti-tail along a near-axial direction, accidentally mirrors design concepts proposed for spacecraft stabilization. It is important to note that similarity in pattern does not prove identity in cause. Nature can and does produce symmetrical structures, and human minds are adept at recognizing order even where none is intended. The documentary approach, therefore, presents these parallels carefully. It describes the triple jets, the equal angular separations, the alignment of one jet with the spin axis and the Sun, and the resemblance to proposed thruster configurations, while also reminding that no direct evidence of control modulation or communication has been detected. The object's motion through the solar system follows a path consistent with gravitational dynamics, and no unexpected changes in trajectory have yet been observed. Nevertheless, the triple jet pattern earns a place among the anomalies that define the case of 3i Atlas. Lists compiled by scientists examining the object's behavior highlight several key features that resist straightforward explanation. The interstellar origin, confirmed by the hyperbolic orbit and excess speed relative to a bound trajectory, is the foundational fact. The presence of an anti-tail, while explainable in broad terms, gains additional significance when combined with the near alignment of the spin axis and the line of sight. The triple jet system revealed by filtered images and persisting over time stands out as the most geometric of the anomalies. Its symmetry is not easily dismissed as observational artifact. Independently processed datasets return the same basic configuration. Different filters and methods of background subtraction still uncover three principal outflows. Slight differences in the exact measured angles may arise from noise-limited resolution or changes in viewing geometry as the object moves along its orbit. Yet the broad pattern of three jets roughly equally separated remains robust. This robustness encourages further scrutiny. Some researchers investigate whether similar patterns might have been overlooked in previous comet observations, perhaps masked by coarser data or dismissed as transient. They reanalyze archival images of well-known comets using the same filters applied to 3I Atlas, searching for evidence of threefold jet symmetry. In a few cases, partial analogs appear, but none match the clarity and persistence seen in the current object. Most comets display more irregular multipolar activity. The rarity of such a clean triple pattern strengthens the sense that something unusual is at work. Other investigators explore the role of internal structure. If 3I Atlas formed in a protoplanetary disk around another star, as most natural interstellar objects are expected to might, its internal layering favor threefold symmetry. Some models of ice and dust aggregation can under certain conditions produce bodies with multiple major lobes or fracturing planes. However, these models tend to generate irregular shapes with few exact symmetries. To produce three jets separated by nearly equal angles would likely require a combination of structural features and an alignment between those features and the present spin axis, which has itself evolved over time under the influence of outgassing and external torques. The chain of events needed to produce the observed configuration remains complex. Against this backdrop of modeling efforts and reanalysis, the public narrative around 3I Atlas begins to change. Early discussions framed the object primarily as a scientific opportunity, a second interstellar visitor, after earlier discoveries promising insights into the composition of material formed around other stars. As more is learned, the emphasis shifts toward its anomalies. Popular accounts mention the anti-tail that inexplicably points toward the Sun, the rotation axis that happens to align almost exactly with the Earth-Sun line during a rare full phase, and now the trio of jets that trace an almost perfect geometric pattern around an unseen nucleus. Each fact can be addressed in isolation by plausible natural processes, yet together they form a pattern that is harder to ignore. For specialists, the triple jet structure becomes a central piece of evidence to be explained. For a wider audience, it becomes an image of strange precision in an otherwise chaotic cosmos. The scientific community continues to exercise caution. Papers under review describe the jets in neutral terms as confined outflows whose separation suggests underlying surface inhomogeneities. They emphasize the need for more data, including observations at different wavelengths that could reveal variations in composition between the jets and the surrounding dust. They call for more detailed, dynamical models that incorporate rotation outgassing and solar forces simultaneously. Yet even within these careful analyses, the regularity of the pattern is acknowledged as an outstanding feature. In internal discussions and private messages, some researchers admit that the triple symmetry lingers in their thoughts as a hint of something beyond the current models. It sits alongside other puzzling aspects of 3I Atlas as part of a small but growing catalog of anomalies. Whether these anomalies will eventually be woven into a coherent natural explanation or will remain as markers of an unresolved mystery is not yet clear. For now the three jets stand like three threads extending from the unknown, inviting the next stages of observation and interpretation. They are neither proof of technology nor mere curiosities. They are structured paths of dust and gas, written into the light, recorded by a space telescope, pointing back to a hidden nucleus, whose true nature remains concealed. Long before the full phase alignment draws global attention, the most visually striking feature of 3i Atlas is already its tail that points the wrong way. In ordinary comets, the main tail extends away from the sun, carried outward by the pressure of sunlight and the flow of charged particles that stream from the star. Gas is ionized and swept into a pale straight plume on the night side, while dust follows curved paths that, when projected on the sky, still fall broadly in the anti-solar direction. This behavior is not merely a habit of comets. It is a direct expression of the basic forces at work in the inner solar system. For 3i Atlas, however, the dominant feature is an anti-tail, a narrow structure that appears to point back toward the sun instead of away. In images taken from Earth, even before the perfect alignment of January, a sunward plume is present. During the full phase, when the alignment with Earth and Sun becomes especially tight, that plume sharpens into a conspicuous feature. It extends along the line that connects the object to the star, and for a brief interval, almost exactly along the line that also reaches the planet. At first glance, this seems to contradict the basic rule that solar radiation pushes material away from the sun. Yet cometary dynamics allow such apparently backward tails under certain conditions. The key lies in the fact that dust grains once lifted from the nucleus do not simply stream straight away from the sun. They inherit the orbital motion of the comet, then slowly drift under the combined influence of gravity and radiation pressure. Over time, they spread into a sheet of particles that lies close to the orbital plane of the comet. When an observer happens to view this sheet edge on the otherwise dispersed dust, can project into a narrow spike-like structure that seems to point sunward even though each grain is still being pushed away. In this sense, an anti-tail is as much a trick of geometry as a physical reversal. Many comets have displayed such features when seen from particular vantage points. In the case of 3i Atlas models that follow the trajectories of dust grains, can indeed produce an anti-tail. Large particles less affected by radiation pressure than fine dust can remain closer to the orbital path and form a dense stream. When the Earth crosses the orbital plane or passes near it, that stream can come into view as a thin sunward extension. The physics is standard and no new forces are required. However, the details still matter. The strength, duration, and orientation of the anti-tail depend on the timing of dust release, the distribution of grain sizes, and the precise shape and orientation of the object's orbit. For a typical comet bound to the sun, these parameters can vary widely, yet still fall within well-explored ranges. For 3i Atlas, the situation is different. The interstellar visitor follows a hyperbolic path through the solar system, arriving from far beyond and leaving again without returning. Its velocity is higher than that of bound comets, and its trajectory is not constrained by the same long-term gravitational interactions that shape local populations. The fact that its path lies close to the orbital plane of the major planets is therefore notable. This plane, defined by the average orbits of Earth and its neighbors, represents a thin disk in which most solar system bodies reside. An interstellar object could, in principle, approach from any direction inclined at any angle to this disk. Earlier visitors have indeed displayed significant tilts. 3i Atlas, by contrast, travels in an orbital plane that almost coincides with that of the planets. As a result, the sheet of dust it creates lies near the same plane that Earth occupies. This alignment greatly enhances the chance that at some point during the passage, the planet will view the dust stream edge-on and witness a pronounced anti-tail. The geometry is simple enough when stated, yet the coincidence of an interstellar trajectory lying so close to the planetary plane is not trivial. Natural processes in the galaxy can send objects inward along many paths, but there is no strong reason to expect a preference for the exact plane in which the solar system's major planets orbit. Thus, the mere fact that 3i Atlas moves in the orbital plane of the planets becomes one entry in the growing list of anomalies. When combined with the presence of a persistent anti-tail, it gains additional weight. Modeling efforts seek to reproduce the observed structure in detail. Researchers simulate dust release at various points along the object's path, assigning different grain sizes and ejection speeds, then integrating the resulting trajectories under the influence of solar gravity and radiation. By comparing these synthetic dust distributions with the real images, they attempt to constrain when and how the material must have been released to generate the sunward plume seen from Earth. In broad terms, the models succeed. They show that a stream of relatively large grains emitted as 3i Atlas approached the Sun can form a plane-aligned structure that, when viewed from the near planetary plane, appears as an anti-tail. However, matching the precise brightness profile length and persistence of the observed plume often requires fine-tuning. Certain combinations of grain size and release time fit one aspect but not another. Adjusting the parameters to extend the lifetime of the anti-tail, for example, may overproduce brightness in other regions or conflict with constraints from polarization measurements. The sense that the anti-tail is both explainable and awkward persists. From the standpoint of classical comet science 3, I-Atlas proves that interstellar objects can display the same kinds of geometric effects as local comets. It confirms that dust dynamics in the solar system are governed by familiar rules even when the source material formed around another star. Yet, within that confirmation lies a subtle friction. The anti-tail is not just a brief marginal feature. It is a dominant structure clearly visible in multiple datasets aligned with a trajectory that already displays unusual properties. Its emergence at the same time as a rare full-phase alignment and a near alignment of the rotation axis with the Earth-Sun line compounds the sense that several low-probability events have overlapped in this one case. Astronomers are cautious in how they describe this overlap. They remind that the solar system has billions of years in which to host such coincidences. Given enough time and enough passing objects, even rare alignments will occur. An observer living when they do happen might be tempted to attach special meaning to them, but statistics alone can account for the presence of outliers. At the same time, they acknowledge that anomalies deserve attention precisely because they may point to new physics, unusual formation histories, or in the broadest sense, arrangements that challenge prior assumptions. In discussions of 3i Atlas, the anti-tail thus becomes both an example and a test. It is an example of how geometry can turn a familiar process into a visually surprising phenomenon. It is a test of how far existing models can be stretched to reproduce an observation without invoking additional factors. As the data accumulate, the anti-tail also becomes a guide. Its shape and orientation provide clues to the timing and directionality of dust release. Combined with the triple jet pattern and the rotation period, it helps to anchor models of the nucleus. If the anti-tail is fed primarily by one jet aligned with the spin axis, then the history of that jet's activity can, in principle, be reconstructed from the dust it has left behind. The plane of the dust sheet traces the orbital plane, which is already nearly the same as that of the planets, while the narrowness of the plume reflects the stability of the jet direction. This stability is easier to maintain if the source is structurally tied to the rotation axis, whether by natural fractures or by some more organized architecture. When this line of reasoning is extended, more speculative ideas reappear. An object that releases material in a controlled fashion along a fixed direction aligned with its rotation axis and orbital plane could, in principle, be adjusting its own motion or encoding information in its outflow. The anti-tail would then be not only a byproduct of dust dynamics, but a visible trace of intentional activity. No direct evidence supports this stronger interpretation. There are no observed modulations that unambiguously signal communication, no abrupt maneuvers, no departures from gravitational trajectories. Nonetheless, the mere possibility that the anti-tail could serve as a channel or signature keeps such ideas alive in certain circles. The scientific mainstream remains anchored in the natural explanation, yet it does not forbid others from considering alternative frameworks provided they are grounded in the actual data. Within that data, the anti-tail holds a firm place. It is measured, modeled, and mapped. Its brightness and polarization are tabulated. Its evolution over days and weeks is followed as the object moves past the Sun and outward toward the orbit of Jupiter. As 3I Atlas recedes, the anti-tail gradually weakens and eventually fades its constituent grains, dispersing into the broader environment of interplanetary space. The plume that once seemed to point accusingly back at the Sun and in a brief moment toward Earth becomes just another thin stream of dust in the vastness. What remains are the records, the images, and the models, all of which preserve the memory of a tail that appeared to point the wrong way at the right time. In the catalog of 3I Atlas anomalies, that memory continues to exert a quiet pull. It is a reminder that even when the governing physics are well understood, the specific arrangements they produce can still surprise, and that in those surprises lie the seeds of deeper questions about how the solar system is shaped, how interstellar visitors move through it, and whether any of them carry more than ice and dust. As models of motion and geometry settle into place, attention shifts toward what 3I Atlas is actually made of and what that material would mean if it could ever reach Earth. Spectroscopic observations taken as the object approached the inner solar system show that, like many comets, it releases a mixture of gases and dust when warmed by sunlight. Among the detected species is cyanide, a molecule well known for its toxicity to terrestrial life. Similar signatures have been seen in other comets from the solar system, but in those cases, the familiarity of the source dulls the sense of threat. For an interstellar visitor whose origin lies in an unknown planetary system, the presence of cyanide and related compounds carries a different weight. It implies that at least some of the basic chemical pathways that produce complex, hazardous molecules operate beyond the sun's domain, and that material from those distant regions can, in principle, drift into the neighborhood of a habitable world. In public imagination, the idea of a cyanide-bearing object swinging through the inner system presents an easy narrative of danger. The visual of a sunward jet that seems for a brief time to aim nearly along the line between the object and Earth amplifies that impression. There is a temptation to picture streams of toxic gas directed toward the planet. The scientific response begins by dismantling this picture with detailed calculations. The nucleus of 3I Atlas travels at a speed of roughly 60 kilometers per second relative to the Sun on a hyperbolic trajectory that carries it past the star and back out into interstellar space. The gas and dust it releases near perihelion, the point of closest approach to the Sun, share this motion initially. Once free of the surface, however, these particles experience additional forces. Solar radiation exerts pressure on dust grains, especially the smaller ones, pushing them away from the Sun. Charged particles in the solar wind interact with ionized gas, sweeping it along magnetic field lines into extended tails. The combined effect is to carry most of the released material outward and away from the inner system, or at least into regions of space that do not intersect Earth's orbit. Orbital calculations that track both the nucleus and the likely paths of its dust envelope show that the object's trajectory does not cross the circular path Earth follows around the Sun. The closest approach between the orbit of the nucleus and that of the planet occurs at a distance that is large compared with the scale of Earth's atmosphere, and the dust grains, further displaced by radiation pressure, are steered into directions that miss the planetary region entirely. Even if a few stray particles wander closer, the density of material is so low that no significant concentration of toxic gas could ever accumulate near Earth. In this sense, the hazard is more symbolic than physical. The presence of cyanide reveals that 3I Atlas carries chemistry that would be dangerous in large quantities, but the dynamics of its motion and the environment around the Sun ensure that this chemistry remains remote. The anti-tail that appears to point toward Earth is a line of sight effect a perspective on a dust sheet rather than a stream aimed with intent. Once this is established, the cyanide becomes less a threat and more a clue. It joins other molecular signatures in defining the composition of the object's volatile inventory. Astronomers compare the relative strengths of emission lines associated with different species to those measured in solar system comets. Some ratios look familiar, suggesting that the fundamental building blocks of volatile chemistry are similar in interstellar and local contexts. Others show modest deviations, hinting at differences in formation conditions or thermal history. For instance, the relative abundance of certain carbon-bearing molecules may be slightly higher or lower than typical values in known comets, pointing to variations in the environment where the nucleus originally condensed. Combined with dust properties inferred from brightness and polarization, these compositional details help build a profile of 3I Atlas as an emissary from another stellar nursery. At the same time, the efficiency with which certain molecules, including cyanide, are released from the surface poses questions. The persistence of strong emission over extended periods suggests active regions where volatile material is exposed in substantial quantities. When these regions coincide with the sources of the triple jet system, the picture that emerges is one of focused, sustained outgassing. The same geometric regularity that defines the jets in the dust domain may also characterize the distribution of gas release. In natural terms, this would imply that the nucleus contains reservoirs of volatile material organized in a threefold pattern, perhaps along fractures or layers that intersect the surface at three main locations. The symmetry of both gas and dust release would then reflect the internal structure of the object. This idea is plausible, yet the exact origin of such an internal architecture remains uncertain, especially for a body formed in another system. Alternatively, if one entertains the possibility of technological involvement, the efficient release of specific molecules along well-defined directions could be interpreted as deliberate. In this speculative framework, cyanide and other volatiles might not be mere remnants of a primordial composition, but byproducts of controlled processes on or within the object. The triple jets would then be channels for expelling waste products or reaction gases with their symmetry and stability arising from engineered design. The anti-tail, aligned with the rotation axis and the Earth-Sun line during the full phase, would be the most prominent manifestation of this system. The mainstream scientific view does not endorse this interpretation, but the structural parallels are noted in quiet discussions. Regardless of origin, the fact remains that 3I Atlas sheds material far more efficiently than a simple inert rock. Its observed brightness, driven by reflected sunlight from dust and emission from gas, indicates a substantial mass loss as it passes near the sun. Through careful modeling of the brightness evolution, astronomers estimate the total amount of material released. While the precise numbers carry uncertainties, the conclusion is that the object loses a non-trivial fraction of its surface layers during this passage. For an interstellar visitor that may rarely approach stars closely, such an episode of intense outgassing represents a significant evolutionary event. In this sense, the object is not simply moving through the solar system unchanged. It is being reshaped by the encounter, its outer layers sublimated and carried away into space. The fate of this shed material offers another perspective on hazard. Though it does not threaten Earth, it enriches the interplanetary medium with interstellar dust and molecules. Tiny grains from another star's environment, now detached from their original host mix, with the constant drizzle of local cometary and asteroidal fragments. Over long time scales, such contributions could subtly alter the composition of the dust that eventually falls into planetary atmospheres. On this passage, the effect is negligible, but over the lifetime of the galaxy, the cumulative exchange between systems may play a quiet role in transporting complex molecules across stellar boundaries. The idea of interstellar transfer of material is not new. Meteoritic studies have suggested that grains formed around other stars can be found embedded in solar system solids. In this context, 3I Atlas provides a direct macroscopic example of such interchange in action. Its cyanide-laden outflow, while no threat to Earth, becomes part of a broader story, in which planetary systems influence one another chemically through wandering bodies. This scientific framing shifts the focus from fear to curiosity. Instead of asking what harm the object might do, researchers ask what it can reveal about the environments where it formed. The detailed spectrum of its gas emissions, the size, distribution, and reflectivity of its dust, and the rates at which different species are released all become clues to its origin. Does it resemble comets that formed in the cold outer reaches of the solar system? Or does it carry signatures of a different kind of disk, perhaps richer in certain elements, or processed under distinct radiation fields? Each answer, even if partial, informs models of planet formation beyond the Sun. Yet it would be misleading to say that the sense of unease entirely disappears. There is a psychological difference between contemplating the gentle fall of interstellar grains over eons and watching in real time a cyanide-containing object sweep through the inner solar system, pointing an anti-tail toward Earth, even if the hazard is illusory. The episode underlines how closely the perception of risk is tied to geometry and narrative. From a purely quantitative standpoint, 3i Atlas is harmless. From the standpoint of story, it brings the outer galaxy into immediate proximity, carrying with it molecules that in a different configuration could be deeply dangerous. In the emergent narrative of this interstellar visitor, the section on toxic dust thus performs a double role. Scientifically, it reassures by showing that the object's speed, trajectory, and interaction with solar forces make a direct impact on Earth implausible. Emotionally and conceptually, it emphasizes that the solar system is not isolated. Material from other stars can and does pass through the region where a living planet orbits, bearing compounds that interact strongly with life. The combination of safety and proximity sharpens the sense of living in a connected cosmos, where distant processes can leave tangible traces. This connection feeds back into the broader question of what 3i Atlas represents. If the chemistry of its gas and dust can be fully explained by natural processes in a foreign protoplanetary disk, then the object stands as a valuable sample of that environment. If, however, some of its compositional features, release patterns, or associations with the triple jet system resist such explanation, they may point to a more complex story, one in which natural and possibly technological factors intertwine. For now, the calculations of safe distance and harmless dispersal stand firm. The cyanide and other toxins it releases dissipate into the vastness, diluted beyond significance. What remains for Earth is not poison, but information carried on spectra and brightness curves, and the lingering memory of a jet that seemed for a moment to aim directly along the planet's line of sight before the object sped on toward the realm of Jupiter. As 3i Atlas recedes from the immediate glare of the Sun and moves outward through the inner regions of the solar system, the focus of scientific attention gradually shifts from its internal structure and toxic outflow to its future path near Jupiter. Calculations performed on the basis of precise astrometric measurements show that in mid-March of the year 2026, the interstellar visitor will pass through a region of space where the gravity of Jupiter becomes comparable to and then briefly dominates over the gravity of the Sun for small nearby objects. This region, sometimes described as the zone within which Jupiter can in principle capture bodies into temporary or permanent orbits, acts as a natural testing ground for any unusual behavior. If 3i Atlas is a purely natural object, its passage through this region should follow the rules of celestial mechanics, modified only slightly by the outgassing forces that also affect comets. If, however, there is any form of controlled activity or hidden architecture, the encounter with Jupiter provides an opportunity for that control to reveal itself in a measurable way. The key date is the 16th of March. On that day, according to the most refined trajectory models, 3i Atlas will pass near the distance at which Jupiter's gravitational pull on nearby small objects surpasses the Sun's. This distance marks the effective edge of the planet's dominion over potential satellites. In broad terms, an object that approaches within this zone can, under favorable conditions, shed material that remains bound to Jupiter rather than to the Sun. For a natural comet or asteroid, this is not an easy feat. Any fragment released in the vicinity of Jupiter must have its relative motion carefully arranged so that a significant portion of its velocity with respect to the planet is canceled. Otherwise, the fragment simply continues on a similar hyperbolic path, perhaps deflected but not captured. 3. I-Atlas itself moves through the solar system at about 60 kilometers per second, a speed that happens to be similar to the escape velocity from just above the cloud tops of Jupiter. This numerical coincidence means that if the object were to skim very close to the visible atmosphere of the giant planet, gravitational interaction could alter its path dramatically, even potentially redirecting it in a way that brings it onto a trajectory that intersects the inner solar system again at a later time. Such a scenario captures the imagination. An interstellar visitor swings past Jupiter, is flung back inward by a gravitational slingshot, and returns toward the region of Earth. However, the actual predicted distance of closest approach tells a different story. Detailed orbit integrations indicate that 3i Atlas will not graze the visible surface or even pass particularly close to the planet. Instead, it will travel at a distance on the order of tens of millions of kilometers, far outside the regime where Jupiter's gravity can impose a dramatic deflection. At such a separation, the planet's influence is still present, but subtle. It can nudge the trajectory, slightly altering the direction of motion by a small angle, but it cannot easily turn a single swift object back toward the inner system. For this reason, astronomers do not expect the nucleus of 3i Atlas to experience a strong gravitational slingshot that returns it to the neighborhood of Earth. Its path remains essentially that of a one-time visitor, arriving from interstellar space, passing near the Sun, and then departing along a new but still hyperbolic route. The importance of Jupiter lies not in its ability to redirect the main body, but in its capacity to serve as a detector and potential collector of smaller fragments that the interstellar object may release. If 3i Atlas sheds secondary bodies as it travels particularly near the time of its encounter with Jupiter, those fragments could in principle be left behind in orbits bound to the giant planet. For a natural rock, this kind of deposition is unlikely. The energy and angular momentum of each fragment relative to Jupiter would have to be tuned in such a way that their forward motion with respect to the planet is significantly reduced. Outgassing alone acting in simple irregular ways is not expected to consistently produce such tuning. For this reason, the formation of new long-lived satellites around Jupiter as a result of a chance encounter with a natural interstellar object is considered extremely improbable. If, however, 3i Atlas were an engineered object or carried smaller devices that could maneuver independently, the close pass by Jupiter could be used as an opportunity to seed the planet's environment with artifacts. In that speculative framework, fragments released with carefully controlled velocities could settle into orbits near the planet, perhaps within its equatorial plane or around its stable Lagrange points, where the combined gravity of Jupiter and the Sun allows small bodies to linger. Such deposits would represent a long-term presence in the system, potentially designed to monitor or interact with the giant planet and its moons. Against this background of possibilities, both natural and speculative, the known spacecraft already operating near Jupiter gain new relevance. The Juno mission, launched by NASA and now in a polar orbit around the planet, continuously monitors its magnetic field, gravitational harmonics, and auroral emissions. Although not designed specifically to search for incoming interstellar fragments, Juno's instruments and navigation team are well positioned to notice any unexpected objects that pass unusually close. In the years to follow, additional missions from the European Space Agency and NASA aimed at exploring the Jovian system and its icy moons will increase the level of scrutiny. The planned missions, known as JUICE and Europa Clipper, are expected to operate in the vicinity of Jupiter around the decade of 2030, mapping its moons in detail and providing further opportunities to notice anomalous small bodies in stable configurations. In the shorter term, however, the primary tools for monitoring the March encounter are ground-based telescopes and space observatories capable of tracking faint objects near the planet's orbit. Astronomers plan campaigns to search for any new points of light near Jupiter that might appear after the passage of 3I Atlas, especially near the Lagrange regions ahead of and behind the planet in its orbit. These regions are already known to host swarms of Trojan asteroids, natural bodies trapped in stable gravitational niches. The appearance of new objects with unusual orbits or of dust streams with properties linked to the interstellar visitor would be notable. The calculations of expected behavior provide a baseline. In those models, 3I Atlas passes through the region of Jupiter's gravitational dominance without releasing any unusually configured fragments. The only change is a small deflection in its overall trajectory, too subtle to matter for its distant future in interstellar space. Jupiter remains as it is with its existing family of moons and Trojan companions. Any deviation from this baseline, such as the appearance of newly bound bodies with orbits aligned in a suggestive pattern, would demand explanation. Even if such satellites are not detected, the March encounter remains scientifically valuable. It offers a chance to measure how the interstellar object's trajectory responds to a well-understood gravitational environment, and to test models of non-gravitational forces due to outgassing. By comparing the predicted and observed path through the region near Jupiter, astronomers can refine estimates of the strength and directionality of jets on the surface. If the triple jet system exerts significant thrust, its cumulative effect on the orbit should become apparent when 3I Atlas moves through a part of space where Jupiter's gravity subtly alters the balance of forces. Deviations from expected motion might then be used to infer additional details about the jet's orientation and intensity. As this phase approaches, the narrative surrounding 3I Atlas gains an element of anticipation. Earlier stages of the encounter with the solar system have already revealed anomalies. The interstellar origin, the orbital plane aligned with that of the planets, the rare full-phase alignment with the Sun and Earth, the anti-tail that points sunward, the triple jet system with its geometric symmetry, and the efficient release of toxic and complex molecules. The passage near Jupiter now offers a kind of natural experiment in which these features may or may not manifest in new ways. If no unusual satellites appear, and the trajectory follows gravitational expectations, the case for a purely natural explanation strengthens even if some details remain challenging. If, on the other hand, small bodies with strange orbits or unexpected dust structures arise in conjunction with the encounter, the anomaly list will expand further. In public discourse, questions about whether 3I Atlas could slingshot around Jupiter and return toward Earth continue to surface. The scientific answer, based on the calculated missed distance and the known gravitational field of the planet, remains negative. The object does not approach closely enough for such a dramatic redirection. The escape speed at the visible cloud tops of Jupiter is comparable to the speed of the interstellar visitor, but that equality only becomes dynamically powerful if the object actually penetrates the region near the planet, where such speeds translate to strong deflections. At tens of millions of kilometers, this condition is not met. Jupiter's pull tilts the trajectory by a modest amount and then releases the object back into interstellar space. Still, the idea of a slingshot persists in the imagination because it captures a true underlying fact. Giant planets are capable of shaping the paths of small bodies, sometimes drastically. In the case of 3I Atlas, the shaping is subtle, more a slight bend than a sharp turn. The encounter underscores that even when dramatic outcomes do not occur, the underlying structures and forces remain in place, waiting for other bodies on other orbits to pass closer and be more strongly affected. For the scientists, watching the March passage is less about hypothetical returns to Earth and more about opportunity. It is an opportunity to test whether the object behaves as a natural interstellar comet should in the gravitational field of a gas giant, to refine non-gravitational models and to look for any evidence of fragments that might behave in non-standard ways. It is also an opportunity to anchor the story of 3I Atlas in a clear timeline. The January alignment marks the full phase over Earth, the period when the anti-tail and triple jets are most clearly studied. The March encounter marks the point when Jupiter's influence is strongest and when any hidden complexity in the object's behavior might have the best chance to show itself. After that, the interstellar visitor will move beyond the immediate scrutiny of most instruments, gradually fading into the dark as it leaves the solar system behind. In that sense, Jupiter acts as a final lens through which the nature of 3I Atlas can be examined. Whether the planet reveals new anomalies or confirms only gravity, the moment of closest approach becomes a hinge in the narrative. Before it, many open questions gather around the object. After it, some of those questions may sharpen, while others may quietly recede. The outcome is unknown at this stage. Only the trajectory is clear, carrying the interstellar body toward a brief crossing of the giant's gravitational realm, and then onward into the night. While observatories refine their models and prepare for the passage by Jupiter, another layer of the 3I Atlas story unfolds far from telescopes and star catalogs, in offices where the language of classification and redaction replaces that of dust and gas. From the perspective of the public, the object is officially presented as a comet-like visitor from another star, interesting but not threatening, a natural body whose oddities are framed as puzzles rather than alarms. Yet behind this simple message lies a more fragmented reality. Some of the most sensitive data sets, particularly those from the newest space telescopes, are not immediately shared. Teams that control access to high-resolution, Near-infrared images, including those taken by the James Webb Space Telescope, keep their data closed while they carry out their own analyses and write their papers. This is a standard practice in astronomy, but in the case of 3I Atlas, where anomalies pile upon anomalies, the delay creates a vacuum that other institutions move to fill. Intelligence agencies in several countries become involved early, not because they habitually track comets, but because they are tasked with anticipating any risk or opportunity associated with objects that cross the orbital plane of a habitable world. In one country, a formal request is filed under laws designed to guarantee public access to government records, asking whether the Central Intelligence Service holds any files on 3I Atlas. The reply is careful and limited. The agency states that it cannot confirm or deny the existence of such materials, a stock phrase with a specific meaning. To those familiar with its use, the phrase does not imply ignorance. It implies that even admitting the existence or non-existence of relevant documents would reveal information considered sensitive. In effect, it says that discussions have occurred, but that their content is not for public release. This ambiguous acknowledgement circulates among researchers and commentators, adding a subtle layer of unease. It suggests that some part of the governmental apparatus has treated 3I Atlas as more than a routine astronomical object, even if no details are shared. Additional signals come from abroad. Toward the end of the preceding year, in a public event summarizing current affairs, the leader of another major nation is asked by journalists what his intelligence services have told him about the interstellar visitor. He responds with a summary that emphasizes the natural interpretation. According to his account, scientific advisors inform him that the object is simply a comet unusual in origin, perhaps, but not technological and not a threat. The message is clear and reassuring, yet the very fact that such a question is posed at a high level indicates that the object has become a topic of interest within that state's security and scientific agencies as well. In different political systems and languages, similar patterns emerge. Intelligence professionals canvass the assessments of astronomers, brief officials on what is known and unknown, and public statements filter these exchanges into simple narratives. Across these threads runs a common refrain: 3I Atlas is most likely natural, there is no direct evidence of alien technology, and there is nothing for the public to fear in immediate practical terms. What is less visible is the degree to which the anomalies that occupy scientific discussions also feature in quieter conversations among analysts. The interstellar origin, the orbit in the planetary plane, the rare full-phase alignment with the Sun and Earth, the sunward anti-tail, the triple jets, with their geometrical spacing, and the approaching passage by Jupiter, enter briefing documents as a list of unusual properties to be monitored. Agencies accustomed to contemplating low-probability, high-impact scenarios treat such features with attention, even if the official line remains cautious. At the same time, a different kind of information flow complicates the landscape. Social media platforms and video sharing sites begin to fill with content about 3I Atlas. Some videos summarize legitimate scientific findings, drawing from public statements and interviews. Others drift into speculation untethered from data-weaving, elaborate narratives about messages from passengers, deliberate avoidance of Earth, or secret communications recorded by unnamed sources. One particular example, produced using advanced generative tools, presents a realistic but entirely fabricated image of a well-known scientist, apparently recounting a contact with beings aboard the interstellar object and their unfavorable judgment of humanity. The video is convincing enough to fool even someone familiar with the real scientist's work and manner. It circulates widely among a certain audience before being exposed as artificial. The incident serves as a demonstration of the new environment in which the 3I Atlas story unfolds. On one side, there are carefully calibrated statements from agencies that admit little yet reveal through their caution that the object has been the subject of internal deliberations. On another, there are scientific publications and conference talks that painstakingly document observations and models while acknowledging uncertainties and avoiding dramatic claims. On yet another, there is a growing ecosystem of fabricated content that exploits the object's genuine strangeness to generate attention, mixing fragments of truth with pure invention. The interplay of these layers makes it difficult for a casual observer to distinguish solid knowledge from narrative artistry. In response, some scientists choose to engage more directly with the public. Recognizing that their interviews can be edited, recombined, or imitated by synthetic media in ways that distort their meaning, they begin to create controlled channels where they present their findings in their own words and formats, archived in ways that can be verified. The goal is not to compete with every piece of misinformation, but to establish stable reference points against which claims can be tested. They view this as part of a broader challenge posed by artificial media technologies to the integrity of scientific communication. 3. iAtlas thus becomes both a subject of astrophysical study and a case study in how complex, uncertain phenomena are discussed in an era when images, voices, and even apparent testimonies can be generated at will. The mismatch between the pace of scientific analysis and the rapid cycle of online content exacerbates the problem. Data from the most advanced telescopes are still under embargo, undergoing careful processing and peer review, when rumors about what they contain are already spreading. Official agencies, constrained by classification rules and the need to protect sources and methods, respond with formulaic statements that, while perhaps necessary, invite suspicion simply because they are so noncommittal. In such a climate, the absence of clear information can seem as meaningful as its presence. From the standpoint of the documentary narrative, this phase of the 3I Atlas story illustrates how knowledge and ignorance coexist. On the one hand, humanity has the capacity to measure the rotation period of a tiny object beyond Mars, to infer the presence of 3 jets separated by equal angles, to model the trajectory of dust grains pushed by sunlight, and to predict a passage through the gravitational sphere of influence of a giant planet years in advance. On the other hand, key pieces of observational data remain behind closed doors for extended periods, and key institutional actors respond to public queries with carefully constructed phrases that reveal neither the extent of their concern nor the depth of their curiosity. The result is a multi-layered uncertainty. The nature of 3, iAtlas itself, remains unresolved, balanced between increasingly sophisticated natural models and a small but persistent space for technological speculation. The nature of the conversation about it is also unsettled shaped by institutions that guard information scientists who strain to explain anomalies without overreaching, and networks of content creators whose incentives are not aligned with the careful calibration of probability and evidence. In this layered environment, even the choice not to release data can be interpreted as meaningful. When some of the first high-quality spectra and images from the newest space observatories are finally published, they will be read not only for what they show about dust and gas, but also for what they reveal about the intervening months of silence. Discrepancies between earlier rumors and later results will be noted. Any gaps, any features that appear only in certain bands or certain epochs will be scrutinized for hints of selection or omission. The quiet involvement of intelligence agencies will be weighed against the publicly mundane content of the scientific papers. For now, this weighing remains speculative. What is concretely known is that at least one major intelligence service has declined to clarify whether it holds material on 3I Atlas, that a prominent foreign leader has publicly framed the object as a natural comet on the advice of his scientists, and that scientists themselves continue to wrestle with an object whose behavior resists easy classification. 3. I-Atlas thus occupies a boundary region not only in space passing between the gravitational realms of Sun and Jupiter, but also in cultural space passing between domains of open science and closed assessment, between validated observation and synthetic imagery. The hidden data and quiet agencies form one more stratum in its mystery, reminding that the path from measurement to understanding is not purely technical. It is also shaped by institutions' incentives and the evolving tools with which humans generate, distort, and verify images of reality. Years before 3I Atlas sweeps into the inner solar system, a quieter line of inquiry is already laying conceptual groundwork for how an object like this might be interpreted. In that earlier work, astronomers consider a simple but provocative question. If technological societies exist in the outer reaches of the solar system or around other stars, could their artificial lights be detected with existing or planned telescopes? The idea is straightforward. Any luminous source, whether a city on a planetary surface or a cluster of devices in deep space, emits light that travels outward, diminishing in brightness with distance. For an object that produces its own light, this fading follows the basic rule that intensity decreases with the square of the distance. For an object that simply reflects sunlight, the situation is different. Its brightness depends both on how much sunlight reaches it and on how much of that light is scattered back toward an observer. As such an object moves farther from the sun, the available light falls with the square of the distance, and the reflected brightness falls with an additional factor, effectively making the dimming much steeper. In practical terms, a self-luminous object remains visible at greater distances than an equally sized object that only reflects light, provided the intrinsic luminosity is sufficient. The earlier studies translate this conceptual difference into concrete numbers. They ask, for example, how bright a city-sized source of artificial light would appear if it were placed in the outer solar system at a distance comparable to that of Pluto. Using the sensitivity limits of the Hubble Space Telescope and similar instruments, the calculations show that a cluster of lights comparable in output to a large terrestrial metropolis could in principle be detected against the dark background, especially in the deepest exposures. The faint glow of such a city would stand out from reflected sunlight because of how its brightness changes with distance and viewing geometry. A reflective object grows rapidly dimmer as it recedes and as its phase changes, while a self-luminous one dims more slowly and does not depend on angle in the same way. Measuring how brightness varies along an orbit could therefore reveal whether an unknown source is reflecting or generating its light. Extending this reasoning, the studies argue that if there were a collection of technological objects beyond the orbit of Neptune, comparable in size and luminosity to human-built structures such as large spacecraft or orbital platforms, they could easily evade detection. The telescopes used to survey the sky for trans-Neptunian objects are tuned to find bodies that reflect sunlight and are at least tens of kilometers wide. A vehicle only a few tens of meters across, even with modest artificial lighting, would be far below the threshold of current surveys, especially if it did not sit on a planetary surface, but drifted through space. Only if such objects produced light on the scale of an entire city would they become detectable with existing instruments, and even then only if observers deliberately searched for the telltale signature of self-emission, rather than assuming that all sources at those distances are reflective. 3. iAtlas enters this theoretical landscape not as a luminous beacon, but as a moving body, whose brightness arises from reflected sunlight and gas emissions. Yet the conceptual tools developed to distinguish reflective and self-luminous sources become relevant as astronomers track its behavior. As the interstellar visitor approaches and recedes from the sun, its brightness changes. Part of this change arises from the varying distance between the object and Earth part, from the changing amount of sunlight it receives, and part from the evolution of its outgassing and dust production. If some component of its emission were due to its own power source rather than to reflected light or gas fluorescence, the pattern of brightening and dimming would deviate from the curves expected for a purely natural comet. In particular, a self-luminous component would not fade as quickly with distance and would be less sensitive to phase angle, the angle between the sun, the object, and the observer. With this in mind, astronomers examine the brightness history of 3 iAtlas with extra care. Data from Hubble, the James Webb Space Telescope, and large ground-based observatories are combined into a single curve that traces the object's light output over time. Within the uncertainties, the overall trend follows expectations for a comet-like body. A steep increase in brightness as it approaches perihelion, steepening further near full phase due to the opposition effect, where shadows between grains vanish, followed by a decline as it recedes and its activity subsides. The rate of fading appears broadly consistent with a source dominated by reflected sunlight and emission from gas excited by solar radiation. No strong evidence emerges for a luminous component that maintains its brightness in defiance of distance. This absence of a clear self-luminous signature argues against the presence of city-scale artificial lighting on or near the nucleus. If an entire face of the object were covered in light, emitting structures comparable to terrestrial urban areas, their contribution would likely be visible in the brightness curve as a slower decline. However, the constraint is limited. Smaller or more efficient sources, perhaps located on the night side or partially shielded, could still exist without significantly altering the global photometric behavior. Moreover, if any technological elements are present, but designed to operate without bright optical emissions, they would naturally evade this particular diagnostic. In a related line of thought, searches are conducted for artificial lights not on the interstellar visitor itself, but in the outer solar system more broadly. Motivated in part by the arrival of 3I Atlas and in part by earlier theoretical work, analysts re-examine deep field images for any point sources whose brightness and variability are inconsistent with simple reflection. They check whether any trans-Neptunian objects show light curves that appear too stable or too bright at large distances. For the most part, no convincing candidates appear. Objects beyond Neptune that have been studied in detail, including Pluto and many smaller bodies, display brightness patterns that match expectations for reflective surfaces. The conclusion is that if a population of luminous technological artifacts exists in the outer reaches of the solar system, it must either be very small, very efficient at hiding its light, or located in regions not yet covered by the deepest surveys. Against this backdrop of null results, 3I Atlas stands out as a different kind of possible clue. It is not luminous in itself, but it arrives from the direction of interstellar space and passes through the very region where earlier studies imagined the potential presence of technological fleets. The fact that it follows an orbital plane aligned with that of the planets rather than cutting sharply across it raises the possibility that its trajectory is not entirely random. A natural origin can produce such a path, but the coincidence is noteworthy. Some speculative models propose that a distribution of technological devices could be parked beyond the orbit of Neptune, lying dormant or operating at low power until a target system displays signs of interest. In such scenarios, a subset of these devices might occasionally be sent inward, perhaps on reconnaissance or maintenance missions. An object like 3I Atlas, with its interstellar speed, triple jets, and planetary plane orbit, would then be a natural candidate for such a device. The lens of artificial lights provides one way to test this idea, but the absence of strong self-luminous signatures in the data tempers the more dramatic versions of this story. Instead, the earlier work on outer system illumination returns in a more subtle role. It demonstrates that the tools to detect bright technological activity at great distances already exist, but that those tools must be applied deliberately with specific hypotheses in mind. For 3I Atlas, those tools show that whatever it is, it does not behave like a city-sized lamp drifting between the planets. Its brightness patterns are consistent with reflected sunlight and gas emission, modulated by geometry and outgassing. The potential for technology, if any, must therefore be sought in structure and dynamics rather than in obvious, luminous display. This conclusion feeds back into the analysis of the triple jets, the anti-tail, and the rotational alignment. If no overt lamps are present, perhaps the signatures of technology, if they exist at all, are encoded in the way the object moves and sheds material. The concept of ghost lights in the outer system remains as a conceptual anchor, reminding that the absence of evidence is not evidence of absence, especially when surveys are not explicitly tuned to search for artificial spectra or unusual brightness laws. It also underscores how close humanity is to being able to test such ideas more rigorously. With future telescopes dedicated to wide-field, deep imaging of the outer solar system, the threshold for detecting small luminous objects will fall. Long-term monitoring campaigns that carefully track brightness and polarization of faint sources could distinguish reflective from self-luminous behavior more clearly. In that context, 3i Atlas appears as an early case study encountered before the full observational infrastructure is in place. It arrives at a time when artificial intelligence tools are transforming how images can be generated and manipulated, when large telescopes are still ramping up their surveys, and when the community is only beginning to integrate the search for technological artifacts into mainstream planning. The result is a partial picture. The anti-tail is mapped, the jets are resolved in filtered images, the rotation is measured, and the trajectory is traced past Jupiter. The brightness history is consistent with natural processes. At the same time, the conceptual framework of ghost lights in the outer system lingers as an unresolved invitation. It suggests that technological activity could in principle be visible across vast distances, yet it also emphasizes how easily modest-sized constructs can hide beneath detection thresholds. For the narrative, this tension becomes part of the larger mystery of 3i Atlas. The object neither announces itself with glaring artificial lights, nor disappears neatly into the category of ordinary comets. It travels along an orbital plane that makes its dust sheet visible as a sunward plume rotates in a way that aligns a jet with the Earth-Sun line during a rare full phase and carries a triple symmetric outflow that recalls engineered control systems. The idea of ghost lights, once a purely theoretical exercise about hypothetical cities at the edge of the solar system, now attaches itself to a real interstellar visitor, not because lights are seen, but because an absence of obvious luminosity does not erase the hints left by geometry and structure. In this way, the earlier calculations about artificial illumination become part of the interpretive backdrop. They remind those watching that the cosmos could contain technological beacons hidden among natural bodies, that the tools to find them are only beginning to be applied, and that an object like 3i Atlas, with all its anomalies, may belong to a larger population of unnoticed travelers. Whether it does or not remains unknown. What is clear is that the question of artificial light in the darkness, once abstract, now feels closer made tangible by a single faint visitor that passes silently through the solar system and leaves behind only a trail of dust and a series of measurements that do not quite settle into a single, comfortable story. As the months unfold around the passage of 3i Atlas, the object's physical journey through the solar system begins to outpace the rate at which its story can be fully understood. The interstellar visitor moves steadily outward, its brightness fading as it leaves the glare of the inner regions and climbs toward the realm beyond Jupiter. Dust settles into stretched filaments that dilute into the general haze of interplanetary space. Gas emissions subside as sunlight weakens and volatile reservoirs retreat into cold silence beneath the surface. In the sky, the object becomes just another faint point among many, then eventually drops below the threshold of most instruments, leaving only archived data as a record of its presence. On Earth, however, the narrative it has set in motion continues to evolve. Observatories complete their first and second passes through the data collected during perihelion, the full-phase alignment, and the weeks that followed. Papers describing the rotation period, the triple jet system, the anti-tail, and the compositional signatures move through peer review. Some findings confirm early impressions. The rotation period remains close to 7 hours. The alignment of the spin axis during the January event nearly along the Earth-Sun line survive successive refinements. The triple jets revealed by symmetric filtering still appear separated by roughly equal angles and persist over multiple observing epochs. The antitail continues to be well described as a dust structure shaped by the object's movement through the solar system and the geometry of observation, though the details of grain size and release time remain subjects of active modeling. Other findings complicate the picture. High-resolution spectra from the newest space telescopes reveal subtle features in the gas emissions that had not been apparent in earlier, lower-resolution work. Ratios of certain molecules differ slightly from those of typical solar system comets. Polarization measurements show patterns that do not fit neatly into existing categories established for local dust populations. None of these discrepancies is large enough to demand a new physical framework, yet each adds a small weight to the sense that 3i Atlas is not simply a familiar object transplanted from another star. It resembles comets, but not completely. It behaves like a natural body, but with a collection of details that strain the boundaries of ordinary behavior. Meanwhile, the encounter with Jupiter passes as predicted. The interstellar object moves through the region, where the planet's gravitational influence could, in principle, capture fragments, but at the large missed distance foreseen by orbit models. No abrupt deviations in the primary trajectory are seen. Within the precision of the measurements, the path remains that of a single body falling through the combined gravity of sun and planet in accordance with celestial mechanics. Search campaigns near the planet's orbit do not reveal an obvious influx of new satellites linked to the passage. The sky around the Lagrange points remains populated with known Trojan asteroids and a few newly discovered minor bodies, none with orbits that clearly identify them as recent products of the encounter. The absence of dramatic outcomes does not end the inquiry. Instead, it sharpens attention on more subtle effects. Teams compare the object's actual trajectory to that predicted by models that ignore non-gravitational forces. Tiny mismatches barely above the level of measurement noise hint at the cumulative influence of the triple jets as they vent material. By inverting these mismatches, researchers attempt to reconstruct the directions and strengths of the jets over time. The resulting reconstructions are noisy, but suggest that outgassing has indeed nudged the orbit slightly consistent with the idea that the object's activity is structured and persistent. In parallel, the social and informational environment around 3i Atlas continues to shift. Some of the deep fake videos and speculative narratives that flourished early in its passage begin to lose traction as firm peer-reviewed results accumulate. The more carefully curated channels run by scientists gain followers who seek stable reference points amid the churn of online content. At the same time, new synthetic artifacts appear, some building on genuine scientific terms, and results to create plausible-sounding but inaccurate claims. A graph showing the object's brightness curve is subtly altered to introduce a fake plateau suggestive of self-luminous power. An animation of the triple jets is edited to imply coordinated pulsing, then shared without context. These fabrications are harder to dismiss at a glance than the earlier, more blatantly imaginative stories because they rest on real data with small but significant distortions. The boundary between authentic measurement and constructed image grows more porous. In response, scientific institutions experiment with new practices. Some adopt cryptographic methods to sign their data releases and visualizations, allowing anyone to verify that a given figure or animation has not been altered since publication. Others establish open repositories where raw or minimally processed data can be inspected directly by those with the skills to do so. The arrival of 3i Atlas thus coincides with an acceleration in efforts to protect the integrity of scientific records against manipulation. The object becomes a catalyst for innovation, not only in astrophysical modeling, but also in how observational truth is preserved and communicated in an era when images can be fabricated with ease. Through all of this, the central scientific questions remain stubbornly open. Is 3i Atlas a purely natural product of another planetary system, its anomalies arising from unusual but ultimately explainable combinations of formation history, internal structure, and orbital chance? Or does it in some way not yet fully articulated embody a level of organization that exceeds what simple natural processes are likely to produce? The interstellar status, the orbital plane alignment with the planets, the rare full phase with the Earth-Sun line, the sunward anti-tail, the triple jets with their near-perfect spacing, the efficient release of toxic and complex molecules, and the precise, though subtle, non-gravitational forces inferred from trajectory refinements all line up as clues. Each clue taken alone can be fitted into a natural framework with sufficient ingenuity. All taken together, they sketch a profile that remains difficult to classify. Within the scientific community, the dominant view continues to favor nature. Models of cometary physics grow more sophisticated, incorporating the specific details of 3i Atlas as boundary conditions rather than exceptions. The object is treated as a case that stretches the range of familiar behavior and prompts refinement of theories, but does not yet overturn them. Nevertheless, a minority of researchers and thinkers hold open a broader interpretive space. For them, 3i Atlas is not just a data point in the distribution of interstellar visitors. It is a hint of a possible category of objects that blend natural and technological features, perhaps created by cultures that shape existing bodies rather than building entirely artificial spacecraft. In such a picture, the triple jets and aligned anti-tail might reflect partial engineering applied to a captured comet nucleus, using its volatile reservoirs as propellant and its natural dust as both shield and signature. No direct observations confirm such a hybrid scenario, yet neither can it be ruled out conclusively given the data at hand. Outside specialist circles, the story condenses into simpler forms. For many 3i Atlas is remembered as a strange comet from another star that passed through the solar system and did nothing overtly dramatic. For others, it remains a symbol of unexplained order in the sky, a quiet challenge to the assumption that all small bodies are mere debris. In both cases, the specifics of jets and phase angles fade, leaving behind an impression of a moment when the cosmos seemed to direct a narrowly aimed structured object along a path that intersected the attention of a technological species. The interstellar visitor does not communicate in any obvious way. It does not change course in response to radio transmissions or modulate its jets in recognizable patterns. Instead, it leaves behind a record of matter and light of alignments and anomalies to be sifted by instruments and minds. In this record, the line between what can be explained and what remains strange is not fixed. As models improve and new telescopes come online, some aspects of the 3i Atlas puzzle may resolve. Others may become stranger as better data reveal finer structure. New interstellar objects will be discovered, some perhaps more ordinary, others possibly even more peculiar. In that expanding sample, the status of 3I Atlas will evolve. It may come to be seen as the first in a class of structured anomalous visitors, or as an early outlier that later events render less remarkable. For now, it occupies a singular role. It is a messenger whose message is incomplete, a case study in how advanced instruments, complex data, institutional caution, artificial media, and human curiosity intersect when a small distant object moves through the shared gravitational field of sun, planets, and minds. The interstellar visitor's dust has already dispersed. Its icy surface has already cooled. Yet the patterns it traced in both space and thought continue to unfold, inviting further attention to the fine line between the natural and the possibly designed, and to the delicate processes by which a civilization distinguishes real cosmic signals from the images it creates for itself.